discussing about the synchronous motor equivalent circuit and the power consumed, or how the power equations are being written for the synchronous motor. That will be the topic of analysis today. Today with the topics to be covered are equivalent circuit of synchronous motor, the phasor diagram of synchronous motor at different power factors, load, power developed in synchronous motor, and the condition for the maximum power output. So the first we'll start with the synchronous motor, which looks to the similar equivalent circuit as a synchronous generator. So you can see you have got the armature resistance and the armature reactance, leakage reactance, and combined it gives the impedance, synchronous impedance of the given motor. The field winding has got a current of IF, so this field winding resistance will be some RF, and that is being supplied from a separate DC source. Now the difference is, now for the synchronous motor, the V supply, the voltage is your input, and E is the EMF induced in the armature, that is the result of the applied voltage. So the impedance of the given motor will be written as ZS is equal to R plus JXS. So the magnitude will be equal to under root of R square plus XS square, and the angle will be tan inverse of XS by R. For synchronous motors, you can write the equation as V is equal to E plus IZS. Substitute the value of the synchronous impedance and you will get the voltage as E plus IR plus JXS, or you can write as E is equal to V minus IR plus JXS. So both the equations are correct. It's only the terminologies, expressions we have changed. Is the first is the voltage equation, the second one is the EMF equation. Now the phasor diagram of the synchronous motor. We are considering cylindrical rotor over here. So the armature current has is IA, and you have got the synchronous impedance as only ZS and synchronous reactance as XS. So there is no consideration of the cylinder pole rotor reactances. That will be studied later in the next lecture. So the you can see over here, V is the applied voltage, then you have got the drop, that is your IRA drop, and then you have got the IXS drop, and you get the induced EMF over here, and the current is lagging behind the voltage by an angle phi. So this is for the inductive loading. This same phasor diagram can be drawn as, first you can take the IXS drop, that is the reactance drop, and then you can add the resistance drop. So it hardly makes any difference. Only thing is that for the analysis purpose, this phasor diagram becomes easier when you take the reactance drop first and then you add the resistance drop to the given voltage. So E will be equal to V cos phi minus IR drop. Okay, this IR is because it is in phase with the current. Therefore, for E, the cosine of the voltage, that is V cos phi minus IR square plus V sin phi, that is in the direction of the current now, V sin phi minus IXS will give you the magnitude of the voltage E. You can take the right angle triangle as OGC, okay, to find out the equation for the given E in terms of voltage and the IR drop and reactance drop. Now over here you have got the phasor diagram at the unity power factor. This means the current is in phase with the voltage. So the IR drop will be just in opposition, and you have got the reactance drop perpendicular to it. So you will get the E is equal to V minus IR square plus IXS whole square from the right angle triangle OBC. So you can calculate it and you will get this equation. This is again, you have in the second figure, you have taken the IXS drop first, that is the reactance drop first, and then you have added the resistance drop. So whatever you are comfortable with, either taking the resistance drop first or taking the reactance drop first, you can do the phasor calculations as per your convenience. Now the next, it is for the leading power factor. The current is leading the voltage by an angle phi. So you have to calculate the resultant voltage, that is OCG can be considered for the calculation of the E. So E will be equal to V cos phi minus IR squared, this drop. So because V cos phi is OF and IR drop is GF, so OG will be equal to V cos phi minus IR, that whole square, and on the y axis you have got the V sin phi plus IXS, because this is your additive over here, so plus IXS square will give the magnitude of the induced EMF in the synchronous motor. Again, in the same figure, you can take the IXS drop first and the IR drop later, and finally the equation will remain the same. The equation doesn't change. Whatever drop is considered first and the other one will be considered later. Now, what are the different torques in a synchronous motor? The different torques in the synchronous motor, or the terminologies which are used, is the locked rotor torque. The locked rotor torque is the minimum torque at any angular rotor position that is developed with the rotor locked with the rotor locked, that is with the field, and rated voltage at rated frequency is applied at the terminals is called the locked rotor torque. This torque is provided by the stator windings. Now, because the basic principle only depends on the locking of the rotor with the stator poles, and therefore this is known as the locked rotor torque. The running torque, the torque developed by the motor under running condition, is known as the running torque. It is determined by the power rating and the speed of the driven machine. Now the pull-in torque is important. The synchronous motor is usually started as the induction motor, and when it runs about near to the synchronous speed under no load condition, DC excitation is applied and the rotor pulls up into step, and it starts rotating at the synchronous speed. So the pull-in torque is the maximum constant torque at rated voltage and frequency under which a motor will be pulled into the synchronism when DC excitation is applied. So that is the pull-in torque, when the motor comes into the from the induction machine speed, it comes to the synchronous speed after the application of the DC excitation. The pull-out torque is the maximum torque which a synchronous motor can develop at rated voltage and frequency without losing the synchronism, because once it loses its synchronism, that is, it's not rotating at synchronous speed due to the increase in the load, the motor stops to rotate. Therefore, that is the maximum value when the motor, without losing its synchronism, it will continue to provide the torque, that is the maximum value of the torque before losing its synchronism, is known as the pull-out torque. Were developed in synchronous motor, that is, we'll consider the cylindrical rotor and not the salient pole rotor. So we'll consider over here, because the V is the applied voltage and E is the induced EMF in the synchronous motor, and E lags behind the voltage by an angle del. So V is equal to V angle 0 and E is now E angle minus del. So that is the major difference between a synchronous generator and a synchronous motor. In synchronous generator, this E was leading the voltage by an angle del, while for an synchronous motor, the induced EMF lags behind the voltage by this angle, this angle as del. Okay, so that is the major difference. So now the voltage equation becomes as V is equal to E plus IZS. Find out the value of the I, substituting the in the polar form, and once you get the final current, because we need to find the conjugate. So for the conjugate, we'll multiply by the minus for the angles, and therefore the angle becomes positive, as the both were angles were negative over here. And once you calculate the I conjugate, we can calculate the different powers. So the input power will be given as SIG is equal to Pig plus JIQ, that is your rectangular form, active power and reactive power. And in the polar form, we can write it as V into I conjugate. I have explained before also why do we take I conjugate, because when you simple multiply the V into I, the angles will be added in the polar form. But we want the phi as, because power is given by Vi cos phi or Vi sin phi, so that angle phi is only possible when we subtract the two angles. That's the reason we take this conjugate over here of the current, so that we get the actual phasor difference between the voltage and the current. So now just substitute the values over here with respect to angles and find out the V into I conjugate. Then there's substitute the value of I conjugate, or you can directly substitute the I conjugate over here and get the total power, then convert it into rectangular form. When you convert into rectangular form, the angle will be substituted by your cos theta plus j sin theta, and you segregate the real and the imaginary part. After segregation between real and imaginary part, you will get the real power input to the synchronous motor. This cos theta is equal to R by Z, so that is being substituted over here, and so the final equation you get it as input power as V square by Zs square R plus Ve by Zs into minus of sine del minus alpha. So because theta is equal to 90 minus alpha, so that is being substituted over here, and for a 3-phase synchronous motor you will multiply it by 3. Now the reactive power input, take the imaginary part from the total power equation, substitute sin theta is equal to x by z and theta is equal to 90 minus alpha. So the reactive power becomes as V by Zs whole square into Xs plus V E Zs cos del minus alpha. For the 3-phase motor, again multiplied by 3. Now the power output of the synchronous motor. The power output of the synchronous motor will be given as E into I conjugate, because the output is now induced EMF. Therefore, E into I conjugate is the power output. Substitute the values in terms of the angles, and E minus del into V by V minus E. So V angle 0 minus E angle del divided by Z angle theta. Now expand this, multiply this, expand this, then take the conjugate of the equation. After taking the conjugate, you will get the final equation. Then convert the polar into the rectangular form, and after you convert into rectangular form, segregate the real and the imaginary parts. Once you segregate the real and the imaginary parts, we'll come to the real output power, that will be given by your Ve by Zs cos theta minus del minus E square by Zs cos theta. Substitute theta as R by Z and theta is equal to 90 minus alpha. So after substituting these values, you will get the output power as Ve Zs sin del plus alpha minus E square by Zs square into the resistance of the given armature. For the 3-phase motor, the output power will be multiplied by 3, because these are the per phase quantities. Now the reactive power output of the synchronous motor, take the imaginary part from the power output equation and substitute sin theta is equal to x by z and theta is equal to 90 minus alpha. Use the trigonometric identity, and you will get the output reactive power equation as V is Zs cos alpha plus del minus E square Xs by Zs. For the 3-phase, you will multiply it by 3. So for a synchronous motor, actual power developed in the motor is POM, and the power available at the shaft will be minus the rotational losses, where rotational losses include the friction, windage and the core losses. So including all the losses, what is the mechanical power developed? If you subtract the losses, you will get the power output at the shaft. So what is the condition for maximum output power at the shaft? Using the output power equation, you can substitute over here, that is, and differentiate it with respect to del, because that is the variable quantity, rest all are the fixed quantities. Therefore, when you differentiate it with respect to del and equate it to 0, you will get the value, because over here these values V, E, ZS and R are all constants. Therefore, it will be only dependent on the term cos alpha plus del, and equating that to 0, we get the condition as del should be equal to 90 minus alpha, which is equal to theta, that is the impedance angle. So the output power will be maximum when load angle is equal to the impedance angle, and substituting the value of the del, you get the equation as output power equation will be maximum when it is VE by ZS minus E square by ZS square into R. That is the maximum power output for a given synchronous motor. Now, if we neglect the resistance of the armature because it is very small, the equation will be simplified and the output power will be only equal to VE by XS, that is the synchronous reactance. So today we have studied about the equivalent circuit of synchronous motor, the phasor diagram under different power factor loading, and the power developed in the synchronous motor, the real and the reactive input power and the output power, and the condition for the maximum power output.